Hello everyone and welcome to this year one presentation on linear relationships. So as a starter, what we've got here is some data where it shows the area of a bacteria which is measured every 12 hours. So that's why the number of days variable is going up by a half each time, and the area is showing us how that area is changing over time. And if we were to plot that data and join up the points with a smooth curve, then we would get a curve that looks like this. And what the biologist wants to do is they want to find what the equation of that curve is. So they look at that curve and they know that they have seen that sort of shaped curve before. And either this curve is going to fit the form y equals a times x to the power of b. So that would be, for example, where you've got maybe x squared or 3x squared, or maybe x4, or maybe 5x4. So the biologist knows that this sort of shaped curve could result in an equation like that, or it might result in an equation like the second version, which is more like our exponential functions that we've been looking at in a previous presentation. Now, of course, normally we would write our equation in terms of y and x, but if you look at the graph that we have drawn for our data, you can see that y has been replaced with a and x has been replaced with b. And so for this data set, our equation for our curve would be in one of these two forms. And today we are going to look at how to find the equation that is modelled by this data set. And we're going to look at how to do that using a linear relationship. So let us presume that the biologist decides that the best fit for the data that we've been given is this form here, A equals A times D to the power of B. So A and D are your variables, and small a and small b are your constants. So they're the values that we're trying to find for our data set, and then we will know what the equation is of this data that we have represented by the curve. So these will only be estimates, of course, because our values are experimental data. It might be that when we have created our equation, the points don't quite fit the model that we are suggesting, but we are hoping that the model that we come up with is a pretty good estimate for the data set that we've got. So as I said earlier, it's difficult to find those values of big A and D using a curve. It would be much better if we had a linear relationship that we could use in order to find those values. So if this data could be changed to show a straight line rather than a curve, it would be much easier to find these constants, and then I could replace the constant values into this equation, and it would give me the equation for the actual data and the graph that you're seeing in front of you now. Okay, good. So the next thing I need to do is learn how to change an equation that is not in linear form, it is in the form y equals a times x to the power of n, into a linear form equation. And the way that I do that is using logarithms. So step one would be to take logs of both sides. Now I'm taking log to base 10 because it's the most commonly used logarithm. And then before we move any further, a common mistake that students make now is that they bring that power of n down to the front and it acts as a coefficient. And the reason why we can't do that at this minute is because that power of n is only attached to the x. It is not attached to the a. So before I bring that power down to the front, I must use another law of logarithms to separate that right-hand side. So the first step is to write that right-hand side as a sum of two separate logarithms. So that's using one of the laws that we looked at last lesson. And now I can bring that power of n down to the front to act as a coefficient. And the reason for doing that is because it's now starting to look more like a linear form equation. So let me show you how. So log to base 10 of y is going to act as my y equals. So I'm representing that as capital Y. Log to base 10 of x is going to act as my x variable. So I'm calling that capital X. And then if we plot capital Y and capital X on the same curve, or log to base 10 of y and log to base 10 of x, we will find that that is our straight line representation. And that means that the other two values, the log to base 10 of a would represent my y-intercept, my c value, because that's the value that's on its own. And if the y-intercept is log to base 10 of a, then I can use my skills in rearranging into an exponential equation to say that if y-intercept is log to base 10 of a, then rearranging that, I would get a is equal to 10 to the power of the y-intercept. So if I can find the y-intercept on my new straight line graph, then I can place it into this equation and it will give me the value of a within my original equation. And secondly, the value of n is going to be represented by the gradient of that straight line that I've drawn, because that's the value that's going to be before the x. So the gradient of my new straight line graph is going to represent the n value in my original equation. And at that point, I will have found the value of a, and I will have found the value of n, and I can take those two values and put them back into the original equation, and that will be my representation of the original data. Now that's quite algebraic, so we will go back to our previous example with the biologist and see how that works with the data that we've got. So if we now go back to our original data, we'll see how that fits in with what we learned about our biologist and the equation that they suggest is appropriate for this data, which was capital A equals A times D to the power of B. So A will represent our Y variable and D will represent our X variable. So we're going to rearrange it in exactly the same way as we just did with the previous example. So I've taken logs of both sides. I'm then separating the right-hand side into two separate logarithms. And then finally, I'm bringing that b power down to front to act as a coefficient. And once again, what we're doing here is we are trying to form a linear relationship. So instead of plotting d against a, I'm going to be plotting log of d against log of capital A. And that will hopefully create a linear relationship. And then from that straight line, we're going to be able to find some values from it, which will allow me to find the values of small a and b. So I first of all need to find my values of log of capital A and log of small d. And you can do that now on your calculators, and you can pause the video now if you like. And then when you're ready to get the values, then press play. And if you've done that, then you get these values. So these are my values for log to base 10 of D. And these are my values for log to base 10 of capital A. So I've now changed my table to those values that I've just found. And what I'm now going to do is I'm going to plot a graph of log A against log D. And if I do that, then what you can see is that I have a linear relationship now. And this linear relationship is going to be much easier to deal with because from this graph, I'm going to be able to find the y-intercept and I'm going to be able to find the gradient. And if I can find those two values, it's going to allow me to find the original values of small a and b, and then that's going to give me the original equation of the data. So first of all, I'm finding the gradient. So I've chosen 2 points on my line, and using the 2 points that you see here, I have a difference in y of 1.2, and I have a difference in x of 0.4, which means that my gradient is equal to 3. And I can also see that reading from my straight line graph, the y-intercept is minus 0.5. So using my representation of my linear form, I can see that my gradient of my graph is going to be the value for b. So my b value is going to be simply 3, and that's my first value found. My second value, which is the y-intercept, is represented on my straight line form as log to base 10 of a. So log to base 10 of a is going to equal minus 0.5 because that's the y-intercept on my straight line graph. And if I now use my conversion to find the value of a, it works out that a is equal to 10 to the power of minus 0.5. So I get a value for a of 0.316. And then to finish off, these two values, a and b, can now go back into my original equation, and I get this equation for the area of the bacteria after a certain number of days. So we can see whether this works or not by checking the data values that were in my original table. So I've chosen one at random, which is when the number of days is 1.5. And if you work this out on your calculator, you get 1.07. So the model, the equation that I am predicting, is finding the value of a of 1.07, and the actual value of a at that time was 1.1. So it's a pretty good representation of the original data. And we've done it, and we've found those values of small a and small b by looking at a linear form rather than the original curve. Okay, good. So the biologist could have chosen the other form of equation that would then lead to a linear form, and that would be an exponential type curve, y equals k times b to the power of x, which could also give a similar shape to the curve that we saw right at the beginning of the presentation. So in the same way, what we have to do is manipulate this equation into a linear form, and the way that we do it is pretty much the same way as we did the previous one. So we're going to take logs of both sides. Again, log to base 10 is the most common. And then again, as with before, I can't just bring the x down as a power. I'm going to separate the right-hand side into two separate logs. And then I'm going to bring that power down and use it as a coefficient. And then this is now in that general form of the linear model. And I just have to see what is going to represent my y variable and what is going to represent my x variable. And then from that, I'll be able to then discover how to find the values of k and b. So again, my y variable is going to be log to base 10 of y, which I'm going to call capital Y. But in this example, a bit different to the last one, the x variable is exactly that. It's my x variable. So I'm going to call that capital X. And then what I will be doing is I will be plotting x along the bottom, and I will be plotting log to base 10 of y up the side, and that will hopefully give me that linear relationship that I'm looking for from my original data. And then from that resulting graph, I can see that my y-intercept, the c value, is going to be based around log to base 10 of k. So if I can find that y-intercept, if I equate it then to log to base 10 of k, I'm going to be able to find my value for k. And therefore, if I rearrange that y-intercept equals log to base 10 of k, that's going to allow me to find k, which would be 10 to the power of the y-intercept. So that's just done the same as we did in the previous slide. That's using my conversion from a logarithmic expression to an exponential expression. And then similarly, my gradient this time is going to be represented by log to base 10 of b. So if I find the gradient on my resulting linear graph, then the gradient would be log to base 10 of b, and then rearranging that into my exponential form, the value of b would be equal to 10 to the power of the gradient. And that's going to allow me to find both the values for b and k, which I would then substitute back in to the original equation in order to find my my equation for the original data. So we'd sub those back in to y equals k times b to the power of x, and that would be my estimate for the equation of the data values that I'd found in the table. So let's go back to the original data that we had at the start of the presentation, and let's presume that the biologist thinks that an exponential equation would be a better representation of the data that we've got. So the equation would be of this form, where capital A represents the y variable and small d represents the x variable, and what we're trying to do is find the constants of A and B. And the way that we're going to do that is we're going to produce a linear model, a linear relationship based upon this equation. So the first thing we would do is take logs of both sides. Then we would separate the right hand side into two logarithms, and then we would bring that power down to act as a coefficient. And so what we're going to be doing is we're going to be plotting a graph where x, the x-axis, is represented by the variable d, so that doesn't have to change, and the y variable is going to be represented by log to base 10 of a. So I have to change my capital A values into log A values. So I'm going to do that now using my calculator. And then when I draw my new graph, I'm going to have d as my variable that runs along the bottom, and I'm going to have my log A, which runs up the side as my y variable. So that's exactly what I'm going to do now. And I'm going to plot those values. And you can see that I don't quite get as good a representation of a linear model as I did in the previous example. But I'm going to draw a line of best fit through my crosses. And this is the linear model that I am going to use in order to find my values of A and B. So again, I'm going to take the gradient of my straight line. So if I take 2 points on my line, then I can work out the gradient by looking at the change in y over the change in x. And as you can see, if I choose these 2 points here, I get a gradient of 0.9. And that is equivalent to my log to base 10 of b, using the model that I am using as my linear relationship. So log to base 10 of b represents my gradient. And if I rearrange that into my exponential in order to find b, I get an answer of 7.94. So that'll be 10 to the power of 0.9. And similarly, I can see that my y-intercept is minus 1.6. And comparing that with my linear model, I can see that that represents the value of log to base 10 of a. And if I rearrange my logarithm equation, then I can find that a is equal to 10 to the power of minus 1.6, which gives me an a value of 0.0251. So I found my values for a and b, and I can substitute those now back into the original equation that my biologist thinks is a good model for this data. And there I have my final equation. Now I can check to see how close that is as a representation. But I find, as we've already discussed, that this is not as appropriate a model as the previous example. You can see that from the fact that I had to draw a line of best fit through the crosses rather than the line actually going through the crosses in almost a perfect straight line like we had in the first example. So although this will give me an estimate for the value of A based on a value of D, it's not going to be as good a model as the previous example. Okay, good. So it's your turn to practice these skills. So exercise 6.1 on page 93. Have a go at the questions in that exercise. If you've got any questions, ask your classroom teacher. And I look forward to speaking to you on the next presentation. Bye-bye for now.